What if you could travel between cities at speeds once thought impossible? China has just unveiled the CR450, the world's fastest high-speed train, capable of reaching 450 kilometers per hour. This technological marvel is a game-changer in rail transport, surpassing even Japan's Shinkansen and Europe's ICE trains. But what makes this train so revolutionary? How does it compare to existing maglev and hyperloop technologies? Let's break down everything you need to know about the CR450, the evolution of high-speed trains. The journey toward high-speed rail began with the invention of the steam locomotive in the early 19th century. The first full-scale steam-powered railway engine, designed by George Stephenson, debuted in 1825 on the Stockton and Darlington Railway in England. These early trains had an average speed of 24 kilometers per hour, which was groundbreaking at the time. By the mid-19th century, steam locomotives could reach 48 kilometers per hour, making long-distance travel significantly faster than horse-drawn carriages. However, steam locomotives had major limitations. They were inefficient, required frequent stops for water and coal, and produced excessive smoke and pollution. The transition to diesel-electric locomotives in the early 20th century improved efficiency, reducing refueling needs and increasing speeds to 64 to 80 kilometers per hour. By the mid-20th century, fully electric trains were introduced, offering smoother acceleration, higher speeds, and lower maintenance. This shift laid the foundation for the development of true high-speed rail. In 1964, Japan revolutionized rail travel with the launch of the Shinkansen, the world's first true high-speed train. The Zero Series Shinkansen, introduced in time for the Tokyo Olympics, operated at 210 kilometers per hour, cutting travel time between Tokyo and Osaka by 4 hours compared to conventional trains. The Shinkansen's success was due to its dedicated tracks, advanced signaling systems, and aerodynamic design, allowing for smooth acceleration and reduced air resistance. Over the decades, Japan continued to refine its bullet train technology, introducing newer models with enhanced aerodynamics and energy efficiency. By the 2010s, modern Shinkansen models such as the N700 series reached operational speeds of 320 kilometers per hour, setting the standard for high-speed rail worldwide. This achievement demonstrated that high-speed rail could be a viable alternative to air travel for distances under 1,000 kilometers, and inspired nations such as China, France, and Germany to develop their own high-speed networks. China, however, took high-speed rail to an entirely new level, building the largest high-speed rail network in the world within just a few decades. Its entry into high-speed rail began with the Shanghai maglev, introduced in 2004. This train, built using German maglev technology, remains one of the fastest commercial trains in the world, reaching a top speed of 431 kilometers per hour. The 30.5-kilometer journey between Shanghai Pudong International Airport and the city center takes just 8 minutes, a testament to the efficiency of maglev technology. However, despite its speed, the Shanghai maglev was limited to a single short route, prompting China to develop its own high-speed rail solutions. In 2016, China launched its first domestically developed maglev train in Changsha, operating at 100 to 120 kilometers per hour. While significantly slower than the Shanghai maglev, this project marked China's ability to develop and manufacture maglev trains independently. The breakthrough in conventional high-speed rail came in 2017 with the introduction of the CR400 Fuxing, which operates at 350 kilometers per hour, the fastest high-speed train in regular commercial operation. This model was entirely designed and built in China, signifying the country's dominance in the high-speed rail sector. Over the past 2 decades, China has aggressively expanded its high-speed rail network, surpassing other nations in both speed and scale. With over 46,000 kilometers of high-speed rail lines, more than the rest of the world combined, China has transformed intercity travel, significantly reducing travel times and boosting economic connectivity. However, the country's ambitions don't stop here. The unveiling of the CR450, a next-generation high-speed train, marks a new chapter in rail transportation, one that could redefine the limits of speed and efficiency. But what makes the CR450 different from its predecessors, and how does it compare to the world's fastest trains? Let's take a closer look. The CR450, a breakthrough in high-speed rail, On December 29, 2024, China unveiled the CR450 prototype in Beijing, marking a significant milestone in the evolution of high-speed rail. This next-generation train is designed to set new global benchmarks in speed, efficiency, and safety. Developed by CRRC Changchun Railway Vehicles and CRRC Sifang Company Limited, the CR450 is expected to be the fastest high-speed rail vehicle in the world once it enters commercial service. Unlike previous models, which gradually increased speed over decades, the CR450 introduces several technological innovations that dramatically enhance its performance. The CR450 has achieved a top test speed of 450 kilometers per hour with an expected operational speed of 400 kilometers per hour. This leap in speed is made possible by significant advancements in train design, aerodynamics, and propulsion technology. One of its key improvements is a lightweight body structure, reducing overall weight by 10%. This reduction is crucial, as lower mass translates to greater energy efficiency and reduced wear on infrastructure. The train's exterior has been engineered with a streamlined, low-drag design that minimizes air resistance at high speeds, allowing it to travel faster while consuming less energy. Another major breakthrough in the CR450 is its reduction in operational resistance, which has been decreased by 22% compared to its predecessors. This improvement results in smoother acceleration, enhanced stability, and lower energy consumption. The train's advanced traction system plays a crucial role in achieving these results. It utilizes a state-of-the-art water-cooled permanent magnet traction system, which significantly improves power efficiency while reducing heat buildup. This system ensures consistent performance even under extreme operating conditions, making the CR450 one of the most reliable high-speed trains ever developed. Safety and monitoring have also been a major focus of the CR450's development. The train is equipped with over 4,000 sensors that provide real-time diagnostics of critical systems, including structural integrity, braking efficiency, and power distribution. These sensors enable proactive maintenance by detecting potential issues before they become critical, reducing the likelihood of mechanical failures. Additionally, the CR450 incorporates an advanced multi-level emergency braking system that ensures rapid and controlled deceleration in case of unexpected obstacles or system malfunctions. Beyond performance and safety, passenger comfort has also been significantly improved. The CR450's new bogie enclosure design reduces vibrations, ensuring a smoother ride. Noise reduction techniques have been integrated across multiple frequency ranges, lowering interior noise levels by 2 decibels. The train also features larger cabin spaces, including expanded storage areas to accommodate bicycles and wheelchairs, reflecting a focus on accessibility and convenience. While the CR450 has set new standards in high-speed rail design, how does it compare to other high-speed train models worldwide? With competing rail systems in Japan, Europe, and emerging hyperloop technologies, understanding the CR450's position in the global landscape is essential. How the CR450 compares to other high-speed trains. Various countries have developed their own high-speed rail technologies, each with unique engineering solutions, infrastructure challenges, and economic considerations. While maglev and hyperloop technologies continue to evolve, traditional high-speed rail remains the most widespread and practical method for long-distance ground transportation. Let's examine how the CR450 stacks up against some of the world's fastest high-speed rail systems. France's TGV, Train à Grande Vitesse, has long been one of the most recognized high-speed rail networks in the world. The system began the operation in 1981, and its TGV POS model set a world record in 2007 by reaching a speed of 574 kilometers per hour. However, this was a test run, and in commercial operation, TGV trains typically run at a maximum speed of 320 kilometers per hour. The CR450 surpasses the TGV both in speed and in aerodynamic efficiency. Another key difference is infrastructure. While the TGV relies on extensive high-speed rail corridors across France and into neighboring European countries, the CR450 is optimized for China's vast, interconnected high-speed network. Additionally, the TGV is constrained by traditional wheel-on-rail limitations, whereas the CR450 incorporates advanced aerodynamics, weight reduction, and high-efficiency propulsion systems to push past conventional speed thresholds. Germany's ICE-3, developed by Siemens, represents one of Europe's most advanced high-speed rail technologies. Introduced in the early 2000s, the ICE-3 operates at 330 kilometers per hour with a maximum tested speed of 368 kilometers per hour. Unlike China's high-speed trains, which are focused on domestic connectivity, Germany's ICE network integrates seamlessly into Europe's international rail system, linking cities across Germany, France, Belgium, and the Netherlands. While the ICE-3 features a lightweight aluminum body and an advanced regenerative braking system, it is not designed for speeds comparable to the CR450. Additionally, the CR450's improved aerodynamics and water-cooled permanent magnet traction system give it a technological advantage in terms of speed efficiency. Spain's AVE Series 103, built by Siemens, is one of Europe's fastest high-speed trains in operation. With an official commercial speed of 350 kilometers per hour, it is one of the few European trains capable of matching China's earlier CR400 Fuxing. However, the AVE's top test speed is 403 kilometers per hour, making it slightly slower than the CR450's 450 kilometers per hour in test conditions. The key advantage of the AVE system is its extensive use of multi-gauge infrastructure, allowing Spanish high-speed trains to connect with standard European rail lines despite Spain's unique broad-gauge track system. In contrast, the CR450 is built for seamless operation within China's vast high-speed rail network, without the need for track conversions. Additionally, the CR450's noise reduction technology and passenger-focused design provide a more comfortable travel experience at higher speeds. South Korea's HEMU 430X, high-speed electric multiple unit, is the country's most advanced high-speed train. Developed as an experimental platform for next-generation rail technology, it achieved a top test speed of 422 kilometers per hour, making it one of the fastest non-maglev trains in the world. However, in commercial service, South Korea's high-speed rail network currently operates at a maximum of 300 kilometers per hour, meaning the HEMU 430X has not yet been deployed at full capacity. In comparison, the CR450 is already progressing toward commercial operation at a tested speed of 450 kilometers per hour. Italy's Frecciarossa 1000, also known as the ETR 1000, is one of Europe's most modern high-speed trains. Built by Hitachi Rail in Alstom, it operates at a commercial speed of 360 kilometers per hour, making it one of the fastest conventional trains in Europe. Unlike the CR450, which is optimized for long, uninterrupted stretches of high-speed travel, the Frecciarossa 1000 is designed for frequent acceleration and deceleration, allowing it to handle Italy's dense rail network. While both trains emphasize energy efficiency, the CR450's lightweight structure, lower operational resistance, and advanced traction system provide it with a technological edge for sustained ultra-high-speed operation. The CR450 is built to be the fastest wheel-on-rail train in the world, surpassing even the most advanced European and Asian high-speed rail systems. While many high-speed trains have been engineered to balance speed, comfort, and energy efficiency, the CR450 pushes the boundaries further by incorporating aerodynamic refinements, advanced braking technology, and real-time monitoring through thousands of sensors. Unlike experimental maglev systems, which require entirely new infrastructure, or hyperloop concepts that remain largely unproven, the CR450 offers a practical and scalable solution for the next generation of rail travel. With its cutting-edge features, the CR450 is setting a new standard for high-speed rail. But what exactly makes it capable of reaching such unprecedented speeds while maintaining safety and efficiency? To understand that, we need to look at the technological breakthroughs behind its design. The technology behind the CR450. The CR450 is more than just a faster train. It represents a major leap forward in rail engineering. Every aspect of its design has been optimized for high-speed performance, efficiency, and passenger comfort. At ultra-high speeds, air resistance becomes one of the biggest obstacles to efficiency. The CR450 incorporates a sharp-nosed, low-drag front that significantly reduces aerodynamic drag. This streamlined design is based on extensive computational fluid dynamics, CFD simulations, and wind tunnel testing. The shape of the nose helps to break through air resistance smoothly, minimizing turbulence and pressure waves, which is particularly important when entering tunnels at high speeds. Another key aerodynamic feature is the advanced bogie enclosure, which is designed to minimize airflow disruption underneath the train. Traditional high-speed trains often experience turbulence and energy loss due to exposed bogies, the wheel assemblies that connect the train to the track. The CR450's enclosed bogie system reduces this aerodynamic resistance, improving both speed efficiency and stability. This innovation not only contributes to higher speeds, but also lowers energy consumption and noise levels. At speeds approaching 450 kilometers per hour, braking technology is just as critical as acceleration. The CR450 features a multi-level emergency braking system, ensuring that the train can stop safely under any conditions. Unlike conventional air or friction-based braking, the CR450 uses a combination of regenerative, eddy current, and mechanical braking, allowing for smoother deceleration while reducing wear and tear on braking components. Regenerative braking also converts excess kinetic energy back into electricity, improving overall energy efficiency. The train is supported by a high-stability bogie system, which is crucial for maintaining smooth operation at extreme speeds. Traditional trains experience vibrations and lateral movement at high velocities, but the CR450's suspension system has been engineered to minimize these effects. This results in not only a safer ride, but also increased passenger comfort by reducing shaking and sudden movements. The CR450's carbon fiber construction makes it significantly lighter than previous models. Carbon fiber is known for its high strength-to-weight ratio, which allows the train to be both structurally durable and lightweight. This weight reduction contributes to lower energy consumption while maintaining the necessary structural integrity for high-speed operation. Another key technological improvement is noise reduction. At high speeds, wind noise and vibrations can significantly impact passenger experience. The CR450 integrates advanced soundproofing materials and aerodynamic refinements, which help reduce interior noise levels by 2 decibels. This makes long-distance travel more comfortable, particularly for passengers in business and economy class cabins. Unlike experimental vacuum tube transport concepts like the hyperloop, which rely on sealed, low-pressure environments to minimize air resistance, the CR450 operates in open air. This makes it a practical and scalable solution compared to vacuum-based systems, which require entirely new infrastructure. The CR450's engineering advancements allow it to achieve near hyperloop speeds while using existing high-speed rail corridors, making it far more feasible for widespread implementation. With its groundbreaking aerodynamics, advanced braking mechanisms, and energy-efficient design, the CR450 is setting a new global standard for high-speed rail. But before it can enter full-scale commercial service, it must undergo rigorous testing to prove its safety and reliability. Let's examine the testing phase and how China plans to bring the CR450 into mainstream operation. Testing and commercialization of the CR450. Before the CR450 can enter full-scale commercial service, it must undergo extensive testing to ensure its reliability, safety, and efficiency under real-world conditions. Given that this train is pushing the limits of conventional high-speed rail, every component must be rigorously evaluated through simulations, controlled test runs, and long-distance trials. China's approach to high-speed rail development has always emphasized gradual evidence-based progression, and the CR450 is no exception. The CR450 has already undergone over 3,000 engineering simulations and 2,000 platform tests, refining its aerodynamics, braking performance, and traction efficiency. These tests focus on multiple factors, including wind resistance, energy consumption, structural integrity, and emergency response capabilities. Additionally, the CR450 has accumulated more than 200,000 kilometers of test distance in controlled environments, allowing engineers to assess how the train performs under different speed conditions and track layouts. One of the most critical aspects of testing is braking efficiency at maximum speeds. At 450 kilometers per hour, stopping distances must be precisely controlled to ensure passenger safety. The CR450's multi-level emergency braking system has been tested under a variety of simulated failure scenarios, ensuring that the train can decelerate safely in the event of an emergency. Another area of focus has been stability at high speeds. High-speed rail is subject to significant aerodynamic forces, particularly when traveling through tunnels or encountering crosswinds. Testing has verified that the CR450's bogie enclosure system and aerodynamic front-end design reduce vibrations and lateral movement, keeping the train stable even at its top speeds. Despite its technological breakthroughs, the CR450 faces several key challenges before large-scale deployment. One major hurdle was its integration with existing rail networks. While China has the world's largest high-speed rail system, not all tracks are optimized for trains operating at 400 kilometers per hour or more. Infrastructure upgrades, such as reinforced tracks, improved signaling systems, and enhanced power distribution networks, may be required to support sustained ultra-high-speed travel. Another challenge is ensuring a consistent and reliable power supply. High-speed trains consume vast amounts of electricity, and at speeds approaching 450 kilometers per hour, even minor fluctuations in power can impact performance. The CR450 relies on an advanced power management system, but widespread commercial deployment will require strengthening China's railway power grid to ensure stable, high-voltage energy transmission across long distances. Safety regulations also present a significant challenge. While China has extensive experience with high-speed rail, introducing a train that operates at speeds beyond any existing commercial model requires new safety protocols, updated emergency response systems, and extensive coordination with regulatory authorities. The CR450 is expected to undergo further refinements and testing before its official commercial launch, with an initial rollout likely on selected high-speed routes. The goal is to introduce the train into full passenger service while ensuring that all safety and infrastructure challenges have been addressed. Beyond domestic use, China is exploring the potential for international expansion of CR450 technology. With ongoing projects such as the Laos-China Railway and the proposed Pan-Asia Railway network, China is actively working to export its high-speed rail expertise. If successful, the CR450 could become a model for next-generation high-speed rail in Southeast Asia, Europe, and beyond. With its cutting-edge technology, record-breaking speeds, and potential to reshape travel, CR450 stands as a testament to China's dominance in railway innovation. If successfully deployed, the CR450 could reduce reliance on short-haul flights, create new economic corridors, and redefine the way cities and countries connect. Will the CR450 set a new global standard for high-speed rail, or will it remain an ambitious domestic project? Let us know your thoughts in the comments, and don't forget to like and subscribe for more insights into the latest advancements in technology.